Hey there, fellow learners. Welcome to the first episode of Learn Math with Python, with yours truly, Rob from Hills Codes. Today, we're diving deep into the magical world of numbers, but not just any numbers. We're talking about the backbone of mathematics, the building blocks of our numeric universe. So, what exactly are we going to unravel today? Well, let me tell you. We're going to break down each number type from a mathematical perspective, from natural numbers to the mysterious realms of irrational numbers. We're covering it all. First up, we've got the natural numbers. Then we'll explore whole numbers, delve into integers, talk about rational numbers, and last but not least, we have the irrational numbers. But hey, enough with the theory. Let's get our hands dirty with some Python examples. I've got some sweet code snippets lined up to demonstrate each number type in Python. Let's get started. Natural numbers are essentially the numbers we use for counting, whether it's apples, oranges, or any other objects. They mark the beginning of our journey into the world of numbers. Some examples include 1, 2, 3, 4, and so on. Basically, any positive whole number you can think of. Now, let's talk about some key characteristics of natural numbers. Firstly, they start from 1 and keep on going, stretching out into infinity. There's no end to the natural numbers, they just keep on marching forward. Secondly, natural numbers don't include 0 or any negative numbers. They're strictly positive numbers, always moving forward, never looking back. Whole numbers are like a bigger group of numbers that includes all the counting numbers, such as 1, 2, 3, and so forth. But there's an extra member in this group, which is 0. So while natural numbers are just the ones we use for counting, whole numbers also include 0. It's a bit like expanding the team to include the concept of nothing or empty. This makes whole numbers a more comprehensive set for describing different situations, whether we're counting items or acknowledging when there's nothing to count. In simple terms, whole numbers are like natural numbers, but they also include 0. Integers are like the versatile tools in our mathematical toolbox. They include both positive numbers, like 1, 2, 3, and negative numbers, like -1, -2, -3. Think of them as the numbers that cover all bases, from counting money to measuring changes in temperature. For instance, when you're dealing with finances, integers help you keep track of gains and losses, whether it's earning £50 or spending -£20. Similarly, when you're checking the temperature outside, integers come into play, whether it's a chilly -5 degrees Celsius or a toasty 30 degrees Celsius. So, in real-life situations, integers are the go-to numbers for handling a wide range of scenarios, making them an essential part of our everyday math and programming toolkit. Rational numbers are like a big family of numbers that includes integers and fractions. So any whole number like 0, 1, or -3 is a part of this family, as well as fractions like 1/2 or -3/4. What makes a number rational is that you can write it as a simple fraction, like a piece of cake divided into equal parts. For example, if you have 2 slices of cake out of 4, that's 2/4, which is a rational number. But it's not just fractions, even whole numbers are considered rational because they can be written as fractions with a denominator of 1. So whether it's a whole number, a fraction, positive, negative, or even 0, if you can write it as a simple fraction, it's a rational number. Irrational numbers are a unique set of numbers that cannot be represented as simple fractions, making them distinct from rational numbers. When written as decimals, their representation is fascinating. They neither end nor repeat in a pattern, which means they go on forever without settling into a fixed sequence. Examples of these intriguing numbers include familiar ones like the square root of 2, the mathematical constant pi, and Euler's number, denoted as E. These numbers are often encountered in various mathematical and scientific contexts, presenting us with infinite and non-repeating decimal expansions. So, irrational numbers stand out for their non-conforming nature, challenging our conventional understanding of numerical representation. Now that we've covered the mathematical theory, let's transition to the practical side and explore how we apply these number types in Python coding. First off, let's delve into natural numbers, the fundamental counting numbers we use every day, like 1, 2, 3, and so on. In Python, we represent them using the int data type. Think of int as a versatile container that embraces all whole numbers, whether positive, negative, or 0, without any decimal parts. Now, let's see this in action with some Python code. We'll declare a variable called natural_number and assign it the value 5. As we execute the code, notice how this natural number 5 is effortlessly represented as an int in Python. You see, in Python, there isn't a specific data type exclusively for natural numbers. Instead, we rely on the int data type to handle both natural numbers and other whole numbers. Whether it's 1, 2, 3, or any other whole number, Python treats them all as integers. Why use int for natural numbers, you might wonder? Well, it's all about simplicity and efficiency. By sticking to the int data type, Python keeps things streamlined, avoiding unnecessary complexity with multiple data types for different kinds of whole numbers. So, while Python doesn't have a distinct data type for natural numbers, the int data type does the job perfectly, providing a straightforward, efficient, and reliable way to work with whole numbers in Python. Now, let's put this theory to the test with another example. A whole number. We'll declare a variable called whole_number and assign it the value 0. As we execute the code, notice once again, the result confirms that this is indeed an int data type. Now, let's broaden our scope to include integers. Mathematically, integers cover not only positive numbers like 1, 2, and 3, but also their negative counterparts and 0. So let's see this in practice with a Python example. We'll assign the value -2 to a variable named integer and print out its data type to see how Python recognizes it. Upon executing this code, we observe that Python recognizes -2 as an integer, which makes perfect sense. But why do we continue to use the int data type for integers? Well, just like with natural and whole numbers, int offers simplicity and efficiency. By relying on int, Python handles all whole numbers, whether positive, negative, or 0, in a unified manner, avoiding unnecessary complexity with multiple data types. So in Python, integers are essential for representing a wide array of numbers from negative temperatures to counting objects and beyond. And with the int data type, Python provides a reliable and efficient means to work with integers in our code, making mathematical operations a breeze. Now, let's delve into the realm of rational numbers. Rational numbers in mathematics are those that can be expressed as a fraction, where the numerator and denominator are both integers, and the denominator is not 0. This category includes numbers like 1/2, 3/4, and even whole numbers like 5/1. Let's see how Python handles rational numbers with an example. We'll assign the value 1/2 to a variable named rational_number and print out its data type to see how Python recognizes it. Upon executing this code, we observe that Python recognizes 1/2 as a float data type, which may seem surprising at first. However, in Python, numbers with decimal points, even if they represent rational numbers, are generally treated as floating point numbers or float by default. But what are floats in Python? Floats, short for floating point numbers, are a data type used to represent numbers with decimal points or fractions. They allow for a wider range of values and operations compared to integers. Floats are used in Python to handle numbers with fractional parts, such as 3.14 or 0.5. Floats are highly useful in many scenarios, especially in scientific computing and engineering, where precise decimal values are needed. However, it's important to note that floats have limited precision due to the way they're stored in computers, which can sometimes lead to rounding errors in calculations. We'll explore this later on. In summary, floats in Python are a versatile data type for representing numbers with decimal points or fractions. They provide flexibility and efficiency in handling a wide range of numerical values, making them essential in various computational tasks. Now, let's shift our focus to another fascinating category of numbers, irrational numbers. These are numbers that cannot be expressed as a simple fraction and have decimal representations that neither terminate nor repeat. Examples of famous irrational numbers include pi and square root of 2. To explore how Python handles irrational numbers, let's consider an example. We'll import the math module, which provides access to various mathematical functions and constants. Then we'll assign the value of pi to a variable named irrational_number and print out its data type to see how Python recognizes it. Upon executing this code, we observe that Python recognizes pi as a float data type. But why use floats to represent irrational numbers? While irrational numbers cannot be expressed precisely in decimal form, Floats provide an efficient and practical approximation for many computational purposes. Python's math module offers built-in support for common irrational constants like pi, allowing us to use them seamlessly in our code. So, while we may not be able to represent irrational numbers with absolute precision in Python, floats offer a practical and effective means to work with them in various mathematical and scientific applications. This flexibility ensures that Python remains a powerful tool for handling irrational numbers and conducting complex numerical computations. Now, let's delve into an important aspect of working with floating point numbers in Python, the issue of rounding errors. Floats provide a convenient way to represent decimal numbers, but they have limited precision due to the way they're stored in computers. To illustrate this, let's consider an example. We'll create two variables, float_1 and float_2, and assign them the values 0.1 and 0.2, respectively. Then we'll add them together and examine the result. Upon executing this code, you might expect the result to be 0.3. However, due to rounding errors inherent in floating point arithmetic, the actual result may not be exactly as expected. So why do rounding errors occur? Well, it all comes down to how computers represent floating point numbers internally. Computers use binary digits, also known as bits, to store numbers, and not all decimal numbers can be represented precisely in binary. As a result, some decimal fractions may be approximated during storage, leading to small discrepancies in calculations. In simple terms, imagine trying to represent the fraction 1/3 or 0.333 recurring with only a finite number of decimal places. No matter how many digits you use, you'll never be able to represent it precisely. Similarly, computers face a similar challenge when representing certain decimal fractions in binary. So while floating point numbers provide flexibility and efficiency, it's essential to be aware of the potential for rounding errors in computations. Understanding this limitation can help ensure the accuracy of your numerical calculations in Python and other programming languages. However, if precision is crucial and you need to avoid rounding errors, Python offers solutions like the decimal module. This module provides support for decimal floating point arithmetic, allowing for precise representation and arithmetic operations with decimal numbers. To demonstrate, let's import the decimal class from the decimal module and create two decimal objects, decimal_1 and decimal_2, with the values 0.1 and 0.2, respectively. Then we'll add them together and print the result. When we execute this code, we'll notice that the result is precisely 0.3, without any rounding errors. The decimal module allows us to perform arithmetic operations with decimal numbers while preserving their precision. So, if you're working with financial data, scientific measurements, or any other scenario where precision is critical, using the decimal module ensures accurate calculations without the risk of rounding errors. It's a powerful tool for maintaining precision in numerical computations in Python. I hope you found this video helpful. If you did, please consider giving it a thumbs up and subscribing to my channel. Stay tuned for more videos in this series coming your way soon.